Hello and welcome to our next lecture on trellis coded modulation. Let us start with a brief outline of today's talk. As we have seen that the d free, which is the free distance, is one of the single most important parameters to characterize a trellis coded modulation scheme, and we would look at some methods to compute d free. Then we go to fading channels. Commonly encountered in wireless communications, and we will see that the TCM design criteria for fading channels is different than normal additive wide Gaussian noise channels. Then we will logically shift to space time trellis codes, which is a logical extension going from TCM, and we look at two distinct scenarios: slow Rayleigh fading scenario and fast Rayleigh fading scenario. We will look at the distance product design criteria for these two cases. Let us do a quick recap. What we have learned so far is the combined coding and modulation. Then we introduced the notion of trellis coded modulation, followed by what we mean by free distance. Then we looked at Ungerboix's heuristic design rules and spent some time looking at the performance evaluation of designed TCM schemes. We can recollect that TCM decoding is done using the trellis diagram, and we use the notion that any transmitted sequence is actually a path in the trellis, and therefore, we have to find out the corresponding path in the trellis in terms of the decoding algorithm, and we do this using the maximum likelihood decoding criteria. And to do so, we use the very well known Viterbi algorithm. We had used earlier the Viterbi algorithm for convolutional codes, but remember TCM is non-linear as opposed to convolutional codes, which were linear codes. So, for DCM decoding, we had realized that soft decision decoding was used, and we employed the Euclidean distance between the coded sequence and the received sequence as a measure to find out the maximum likelihood sequence, and the Viterbi decoder tries this measure to find the most likely path in the trellis. So, we are using Euclidean distance as opposed to Hamming distance, which was used for the convolutional encoder decoder case. We looked at some performance measures, and we talked about d free as the free Euclidean distance, and we also talked about the n free, which is also a function of d free, is in terms of the average number of paths in the trellis with free Euclidean distance d free. This number is used in conjunction with the evaluation of the error event probability. Then we went on to define this probability of error in terms of the scalar transfer function T d. We have learned how to calculate T d using a modified state diagram, and we figured out that finally we can upper bound the error event probability P by this following expression. And if you look at the asymptotic estimate on the error event probability, we get the following expression: probability of error approximately half times n as a d function of d free error function complement under root d free squared over 4 n naught. So, from that we went on to discuss the bit error probability, and we showed that it can be written as a derivative for this modified t as a function of d and I. So, here t d comma I is the augmented generating function for the modified state diagram. Again, when we had talked about convolutional code, we had introduced this function called augmented generating function. Now, what is important is to find out that the same function can be used to get an upper bound on the bit error probability. Here the derivative is evaluated I is equal to 1 and d is equal to e raised to the power minus 1 over 4 n naught. A tighter upper bound can also be obtained for the bit error probability and is given by the following expression. So, you see that d free is figuring prominently in all of these expressions, again establishing the fact that it is the single most important parameter. Of course, for the probability of error expression, the noise power also starts figuring in the expressions. Now, since d free is such an important parameter, we spent a few slides talking about computing the d free. Okay. Now, please note that this statement is correct when we are talking about additive wide Gaussian noise channels. When we go to fading channels, we will have a slightly different parameter that we will shortly talk about. So, the generative function can be used to calculate the Hamming d free distance earlier. Now, the transfer function of the error state diagram T d also includes information about the distance of all paths in the trellis from the all 0 paths. So, the question is, can we use that information to calculate d free for our case? But the question is, d free may or may not be available in a closed form expression all the time. In the event that T d is obtained in a closed form, the value of d free follows immediately from the expansion of the function in a power series. We have seen that earlier. Now, if you see, if you do not really have a closed form solution, you can write as an expansion as follows. We had seen this earlier. Well, it comes directly from the closed form expression, but in general we can write like this. So, what we do is T d is nothing but the number of paths with d free times this shows that the d free is obtained for these paths, and then there is a next expression where this is d free plus something. So, it is the d next, okay, and this n d next corresponds to the number of paths that contribute to those d next. Okay. So, d next is the second smallest squared Euclidean distance. So, the smallest exponent of d in the series is in the expansion is d free, but we have made this point earlier that we may not have a closed form expression all the time, and one has to resort to numerical methods.
So, what is this d next exactly? I mean, will it be some d free plus 1, then it will be d free plus 2 or something?
Okay, the question being asked is, what is this d next? So, clearly d free is not an integer this time. Had it been the Hamming distance measured and we had taken in convolutional code the generating function T d, then this d raised to the power, if this was 5, then d next could be 6 or 7. But in this case d free could be 3.722, and then the d next could be 4.312, some value which is the next larger value. So, we have no constraint on this being integers here, because we are talking about the free distance of a trellis coded modulation scheme. So, whatever it is, in general there will be some larger distance, and this should correspond to certain number of paths that lead to it. So, those, suppose there are 4 paths which contribute a distance, Euclidean distance, which is d next, then n as a function of d next times d raised power d next, and then there will be a next term which will be d next plus next, and so on and so forth. So, let us consider the function phi I 1 as a function of d as log of the ratios T E d over T d, all right. Now, if you see this phi 1 d decreases monotonically to the limit d free squared as d tends to 0. Therefore, we have an upper bound on d free squared provided d is greater than 0. In order to obtain a lower bound on d free squared, consider the following function phi 2, which is the ratio of log t raised to the power d, log t as a function of d divided by log of d. So, we have this function phi 1 and phi 2, and we will use them to get an estimate of d free. So, if you take log on both sides of the equation that we saw just now, then we have ln d, and the d free squared comes in front, and then we have this expansion going up next. So, if we take d tending to 0 and d greater than 0, we would get roughly ln t as a function of d divided by ln d. This comes to d free squared minus epsilon d. So, the point is, if we can make this epsilon d as small as we can, right. So, then we can have a very good estimate on squared free distance. So, we take smaller and smaller values of epsilon d, and we can get values which are extremely close to squared free distance. So, this is one way to determine or at least get an estimate of squared free distance from the generating function T d. So, couple of things that we must keep in mind while talking about d free. So, the squared free distance is the single most important parameter to determine the quality of a TCM scheme. So, if we have to compare two schemes, the first thing we should do is to compute d free. Please note, d free calculation does not have to be done from the all 0 path, because we are dealing with a non-linear code here. However, two other parameters are also important. The error coefficient n as a function of d free, which tells us that how many paths which are there in the trellis which contribute to this d free. So, question is, d free appears to be the weakest link in the chain. How many weak links are there in this chain? Okay. And after d free, it is not always that we will always be in a bad shape, that we always get an error between the two closest paths. We can also have the d next coming into play. So, the second smallest Euclidean distance between two paths forming an error event is also important as a second order effect. Now, question is, how far are d free and d next? If d next is pretty large with respect to d free, then d next should stop mattering. However, if d next is pretty close, why are we having this discussion while we did not have this for convolutional codes? That is because the d next for the convolutional coder was always an integer away. So, if d free was 2 or 4, then the d next would be at least 1 or 2 more, but we can have d free as 5.3 and d next could be 5.4. So, they can be fairly comparable to each other. So, if d next is very close to d free, and it can be as close as you want or your luck may have it, the SNR requirement for good approximation on upper bound on PE may be large. Now, so far we have only talked about free distance and additive wide Gaussian noise channels, and we have found out that the best strategy is to maximize the free Euclidean distance for the code. But things may not be the same for fading channels. So, let us quickly talk about TCM design for fading channels. Before that, let us take a minute to quickly recap what do we mean by fading channels. So, if you consider a transmitter and a receiver, then we have the signals going from the transmitter to the receiver. However, it is possible that it reaches the receiver through reflections, and the reflections can come from many kinds of objects. So, you could have different buildings or other reflectors, which will lead to the signal reaching from the transmitter to the receiver through multipath. So, currently we have drawn a scenario where we have multipath propagation. But the interesting thing is, when a signal reaches from the transmitter to the receiver through several paths, they add up at the receiver coherently, in phase, out of phase, in such a manner that the resultant vector gives the actual value of the signal received. Now, because of these paths reaching the receiver with delays, because longer path means more delay and hence a phase shift, that means that they can add up and have a destructive interference also, leading to the loss in the signal strength. So, if you plot on this axis the distance from the transmitter to the receiver, and if you look at the power received and make a plot of the power received, and if you do a logarithmic plot, you will have something like this. What it means is that, so if this is some kind of a plot in dB, so we can normalize this. So, if you see that even though as you move away from the transmitter and there appears to be a general downwardly trend, in the short term there is major fluctuations in the received signal, and this is because that the signals received here add up destructively and the vector sum gives a very low value. So, this is typically a profile of a fading channel, and these are your fades. And if this is the receiver threshold over which the signal should work, then there would be many times when you go below the threshold and you may have a loss in communications. So, this is the general nature of the fading channel, and we would like to design our TCM scheme based on the characteristics of a fading channel. Now, if there is a line of sight here, then we know that this is a Rician fading channel. However, if there is no line of sight, then we go to Rayleigh fading channel. So, we will look at these scenarios separately. We come back to our slides now, and we observe that fading channels are frequently encountered in radio and mobile communications, and the cause of fading is the multipath nature as we discussed just now, and this is because the receiver gets signals from different paths with different path delays, and if the signals add up in phase or out of phase, then the net received signal exhibits a random variation in amplitude and phase, which are the sudden drops are called fades. So, we now talk about TCM for fading channels. Let us consider the performance of Trellis coded Emery phase shift keying MPSK over a fading channel. All right. We know that a TCM encoder takes in an input bit stream and outputs a sequence of symbols. In this treatment, we will assume that each of these symbols SI belong to the MPSK signal set. This is clear, we have done this before, and we will use a complex notation. So, each symbol is represented by a point on the complex plane. Now, the coded symbols are interleaved in order to spread out the burst errors caused by slowly varying fading process, and these interleaved symbols are then pulse shaped for no intersymbol interference. So, those are the nitty-gritty details for communications, but we will focus pretty much on the fading characteristic of the channel. Now, the channel corrupts these signals by adding a fading gain, right, and it also has additive wide Gaussian noise. So, the fading gain is a multiplicative gain. So, at the receiver end, the received sequences are demodulated and quantized for soft decision decoding, and in many implementation the channel estimator provides an estimate of the channel gain. So, we would either have the channel state information built into it, or sometimes we will have to go without it for cheaper designs, and then we say the CSI, the channel state information, is not present. So, there are two distinct scenarios. So, at any instant I, time instant I, the received signal R I is equal to G I times S I. S I is the transmitted signal, G I is the multiplicative gain, which is the fading coefficient, plus the noise N I. This is a very simplistic model that we will be using for our case. So, starting with R I is equal to G I into S I plus N I, we say that N I is a sample of the 0 mean Gaussian noise process with variance N naught by 2. G I is the complex channel gain, right, which is also a sample of a complex Gaussian process. So, the G I can be written as A I times e raised to the power j phi I, because G I is complex gain. It not only changes the amplitude, but also the phase. Remember, S I is complex. So, complex into complex gives another complex. So, A I and phi are the amplitude and phase processes respectively, and they can be modeled differently. For example, depending upon whether you have a line of sight or not, A I could be Rayleigh or Rician, and phi I is typically uniformly distributed over 0 to 2 pi. So, let us see if we can start with some assumptions. Let us say that the receiver performs coherent detection, not a bad assumption. Interleaving is ideal. So, we have the fading and amplitude are statistically independent, and the channel can be treated as memory loss channel. So, we have R I is equal to A I into S I plus N I, and we know that for a channel with diffused multipath with no direct line of sight communication between the transmitter and receiver, the fading can be rightly modeled as Rayleigh distributed. So, we write the PDF of the Rayleigh fading channel as follows. For the case where there exists a direct path in addition to the multipath, Rician fading is observed, and the following expression gives the PDF of the Rician fading. Now, K is the Rician fading parameter, and we will define it shortly, and I is the 0 ordered modified Bessel function of the first kind. So, this K will play an important role, and let us understand what K is. K is the Rician parameter. What is it? It is the ratio of the energy of the direct component of the signal to the diffused multipath component. All right. So, if you go back to the diagram we drew and we talk about the direct path. So, there is a certain amount of energy that is coming through the direct path called the line of sight, and then there are so many other reflected paths which are carrying this energy to the receiver. So, the ratio of the energy coming from the direct path to the non line of sight, the diffused path, is the parameter K. So, clearly if there is no line of sight, then K is 0, and so K is equal to 0 implies that we are looking at a standard Rayleigh fading channel. So, a special case K is equal to 0 comes back to the Rayleigh fading distribution. So, now let us look at the performance of a TCM scheme over a fading channel. Let us say that the received signal be R1, R2 up to RL, this is a vector. The maximum likelihood decoder, which we will say will implement using the Viterbi decoder, chooses the coded sequence that is most likely to correspond to the received signals. So, this is achieved by computing a metric between the sequence of received signal RL, here is the received signal, and the possible transmitted signals SL. And we have seen that metric is related to the conditional channel probabilities. So, this metric we can take as log of the probability that RL, this vector, is received given SL is transmitted. So, now we can say that we have access to the channel state information. So, the fading coefficients are known. So, at least the estimates are given. So, this metric also has RL comma SL semicolon AL hat, right, and this is the metric that comes in. So, we have the probability of RL given SL and I have got the estimates, right. So, under the assumption that the ideal interleaving is happening, we can assume that the channel is memoryless. So, each symbol do not have any implication on the subsequent symbol. Therefore, we have this product, because if they are independent, then the probabilities would multiply, but since there is a log, now there is a summation there. So, we have now I is equal to 1 through L, ln P RL given SL, because we have declared that each symbol received is independent of this earlier symbols. And if you have the channel state information, you can write the summation I is equal to 1 through L ln P RL given SL comma AL hat. So, these are the two metrics with which we will work. Now, first we consider the scenario when the channel state information is known correctly, right. So, the metric can now be written as minus RI minus EI SI, because AI is known, right. So, received, and we have to see whether SI into AI, and this is the distance measure we have. So, the pairwise error probability P 2 between SL and SL hat is given by E A L. This is the expectation operator, statistical expectation operator, and this is P 2 SL comma SL hat given A L. And what does this P 2 stand for? Well, it talks about this sequence SL and SL hat, which is the estimate given the channel state information, as the metric of SL hat, right, with RL greater than or equal to between RL and SL. So, how do I choose the most likely? So, wherever this maximizes the metric, given of course this one. So, it is pretty straightforward if you write it out. So, we use Chernoff bounds, and we can write the upper bound on the pairwise error probability as follows. So, this is the pairwise error probability between SL and SL hat. This is the expression that comes out, where k is the Rician parameter. So, if you see for high SNR scenario, right. So, well, this is low. So, this expression is large, and you can neglect this. So, in the denominator you are left with this. So, you can write out P 2 SL comma SL hat as a product, where here this eta is the set of all I for which Si is not equal to Si hat. Okay. So, that is why we are talking about the error probability. So, let us denote the number of elements in eta by ln. So, L eta. So, we are defining this term L eta. What is L eta? Where is the number of elements in this? So, number of cases where Si is not equal to Si hat. So, error happens. So, if you write it down, then from here you can see in terms of the product, I is an element of eta, therefore, you get here raised to power L eta, because only those number of terms multiply. So, you have got this expression now. So, it brings us to a very interesting conclusion. You can see that we have introduced this term dp squared as a function of L eta. What is dp squared? dp squared is the product of this squared Euclidean distance where I is an element of eta, all those paths where you do not have S I is equal to S I hat. So, this dp squared is the squared product distance of the signal S I not equal to S I hat. This will be a very important parameter for fading channels. Specifically, we are talking about Rician fading channel. So, the term L eta is called the effective length of the error event S I not equal to S I hat. We will use these two extensively for the next few slides, but it is so happens that from the derivation we have come to this product, the squared product distance. So, if you talk about the high SNR situation, you can write it the upper bound as P e less than or equal to this summation over this effective length and summation over all the dp squared with effective length, and then you have this expression where this first term alpha as a function of effective length and squared product distance is the average number of code sequences having the effective length L eta and the squared product distance dp squared. So, please note we are doing sequence by sequence decoding, and we have come across a set of sequences which have the effective length L eta and a corresponding squared product distance dp squared. So, the error event probability is actually dominated by the smallest effective length L eta and the smallest product distance dp squared. So, this is an important observation. So, let us denote the smallest effective length by L and the corresponding product distance by dp squared L, okay, since these are the two important parameters which dictate the error event probability. Then asymptotically the error event probability can be written as approximately P e alpha, we have talked about this, and in the numerator we have 1 plus k e raised to power minus k raised to power L. This corresponds to the noise power and squared product distance. So, the effective length L and the squared product distance prominently figure out in the error probability expression. And so, we should have our design criteria based on these. So, we have taken down the same expression on this slide and we make the following observations. So, the error event probability asymptotically varies with the Lth power of SNR, here this term Lth power of SNR. This is similar to what is achieved by time diversity techniques. This is very important. So, this observation tells me that here we are getting a diversity gain because of the TCM scheme, right. So, L is also called the time diversity of the TCM scheme. We are not explicitly using any time diversity schemes. If you remember, time diversity means that you can transmit the same information in different instances in time, assuming that the spacing between these times is not correlated and you get time diversity gain. Here L is the time diversity of the TCM scheme, simply because we have an effective length L, and so our design criteria should be such that we maximize this effective length L so as to gain time diversity in terms of the TCM scheme. The important TCM design parameter are the time diversity L and the product distance dp squared. So, we will use them for our design or comparison of two TCM schemes in fading channel. Please note, we are not talking about d free. There are two different parameters that we have come across. One is the time diversity L and the other is the product distance dp squared. This is in contrast to the free Euclidean distance parameter for the additive wide Gaussian noise channel. So, what works for fading channel may not work for AWGN channel and vice versa. So, this observation we have made, and for large values of the Rician parameters k, the effect of free distance on the performance scheme becomes dominant. That is because if you go to very large value of k, then it starts resembling the AWGN channel, the diffused components wither away, and there is pretty much a line of sight, direct line of sight between the transmitter and receiver, and the Gaussian noise plays dominant role, and therefore, free Euclidean distance becomes important. You can also see that when k becomes large, this term kinds of vanishes, and we are pretty much left with the Euclidean distance part. Now, at low SNR, things again change, because now at low SNR part, this component, right, will start playing a role, and then you will have, even though the value of k is not large, then the SNR starts playing this role. Okay. So, again the free Euclidean distance becomes important for TCM design. So, let us look at the basic design rule for TCM for fading channels at high SNRs and small values of k. Okay. Why small values of k? If the k becomes too large, then it is no longer really mimicking a fading channel. What are the design rules? Maximize the effective length L of the code and minimizing the minimum product distance dp squared. Okay. These are the two design. So, if you consider a TCM scheme with effective length L and the minimum product distance dp squared, suppose that the code is redesigned to yield a minimum product distance dp squared with the same L, then increase in the coding gain due to the increase in the minimum product distance is given as follows. Okay. So, this is the coding gain, and we have the same effective length, but the product distance changes. So, if you have been able to decrease the product distance, that means your gain will improve, and therefore, you can have a relative coding gain as follows. So, here the parameter alpha, alpha 1 and alpha 2 are the average number of code sequences with effective length L. So, it also matters how many sequences in the Trellis diagram have that effective length. So, we observe that for a fixed value of L, increasing the minimum product distance corresponding to a smaller value of L is more effective in improving the performance of the code, okay? Because here the smaller value of the L will give you a better. So, on one side you have to increase L, but when you have tweaking the code, then the gain will be more if the increase is for a smaller L, because L is also here. And please note that the product distance squared is in the logarithm, whereas this is inversely proportional. Now, so far we have assumed that the channel state information was indeed available, but we can carry out a analysis when the CSI is not available. So, what will change is the metric. Earlier we had alpha here, the gain parameter, now we do not have. So, the best bet is Ri minus Si. So, this is the metric we define. So, we can do similar mathematical analysis and we can get this pairwise error probability upper bounded by the following expression. Okay. Again, the effective length and k show up prominently in the expression, but here please note that we have dp raised to power 4. Okay. So, it is even more sensitive here. So, the error event probability p can be determined for this case when the channel state information is not available. So, with that we kind of lay grounds for our next step, which is called the space time trellis codes, which is in one way an extension of trellis coded modulation schemes. But what we do is we now look at expressions and cases where we have two transmit antennas. So, if you see, earlier we had only one antenna. So, we had a trellis, an input sequence came in, we looked at the trellis, on each branch we had a single symbol labeled and the transmitter transmitted it. What if we label every branch with a pair of symbols? So, we have now two transmitters. So, symbol 1 is sent from transmitter 1 and symbol 2 is sent from transmitter 2. It is a very logical extension, and I can extend it to n antennas, NT antennas standing from n transmit antennas. So, what happens if we do this? Okay. This kind of a scheme is called space time trellis codes, because we also not only use the space coordinate, but also time coordinates. So, in different time instances we have different pairs being sent from transmitter 1 and transmitter 2. So, we are curious to finding out what happens. So, now we go to multi antenna systems. Okay. So, we have TCM schemes where every branch is labeled with NT signals. In this example, there are two transmit antennas. So, every branch will have two symbols. If I have NT transmit antennas, I will have NT symbols. Okay. Let us look at a very simple example. So, there are 4 states in this trellis, and it is sufficient to draw the first portion of the trellis diagram, because it will repeat infinitely after this. There are 4 emanating branches from every node. So, there should be 4 labels here. Now, this is symbol S0, S1, S2, S3. So, this is a 4 PSK constellation QPSK. Now, in a normal TCM schemes, each branch would be labeled with either S0 or for short 0, S2 or 2, S4, or here it is QPSK. So, S0, S1, S2, S3. So, they will be labeled here. But here you see there is a pair. So, 0 means if this branch is to be traversed, then transmit antenna 1 should send S0, transmit antenna 2 should send S0. If we go on this branch, then transmit antenna 1 should send S0, transmit antenna 2 should send S1, and so on and so forth. So, this is a mapping scheme. So, if the label is C1, C2 for any edge, then C1 is transmitted from antenna 1 and C2 is transmitted from antenna 2, a very simple extension of the TCM scheme. So, for decoding we would use vector Viterbi decoding, right, and we can assume that channel state information is present at the receiver, and let us see how do we define it. So, assuming that Rj is the received signal at the received antenna j at time t, and alpha ij is the path gain from the transmit antenna I to receive antenna j, and branch metric of the transmission is labeled as follows. So, this is q1t, q2t dot 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 up to qt. So, then we have all the path gains in the transmission path times the received signal and minus RTJ. So, the Viterbi algorithm is used to compute the path with the lowest accumulated metric. So, please note what we are doing is defining the metric slightly differently, taking into consideration both or all the NT signals that are transmitted. So, consider a generic encoder structure for a full rate MPSK STTC space time trellis code, right. So, what we will do is in the next slide we will look at the generic structure of this, and it will be better to start with the circuit diagram and or a block diagram of this encoder first. So, we have C1, C2 up to Cm coming in, and then we have these coefficients that we just now looked at, they are multiplied and then they add, and then this is what is sent out. This Gk is represented by as follows. So, this is the general encoder structure for a space time trellis code. Okay. So, the what we can do is we can use that diagram to understand that the multiplier outputs from all the shift registers are added modulo m and will give the encoder output as follows: x1 x2 dot 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 up to x n raised by n t, and the total memory order of the encoder is denoted by nu is as follows. So, we have two conditions, slow Rayleigh fading and fast Rayleigh fading. So, if you consider the slow Rayleigh fading, so for each symbol the space time encoder generated NT code symbols C1, C2t up to CNTT, which are simultaneously transmitted from the NT transmit antennas that we have seen. Now, we define a code vector as follows, right. So, this is the code vector sequence which is transmitted, and the ML decoder decides to erroneously find the C tilde as follows. So, transmitted sequence, received sequence. So, frame of length j is considered. So, we have now an error matrix as follows, which is an NT cross NT error matrix A, and we will use this for our design criteria. What is A as a function of C and C tilde? C was sent, C tilde was received. It is, we define it as CT minus C tilde times CT minus C tilde complex conjugate. So, if ideal chance state information is available at the receiver, then it is possible to show that the pairwise error probability of the erroneously detected signal is given as follows. So, we do not go for the derivation, but this is the pairwise error probability that C was sent and C tilde was received, or at least decoded incorrectly, as follows. And we find very interestingly that the eigenvalues of the A matrix come into picture. NR is the number of received antennas, right, and R is the rank of the error matrix A, which we had defined previously. So, based on this, to minimize the PEP, which is the pairwise error probability, we have to play with the NR and R, the rank, right. So, rank has to come into picture. So, please note that the diversity gain is given by, so this is the effectively the SNR. So, diversity gain of RNR is obtained, and the coding gain is given by the product of all the lambda i's, which is the eigenvalues of A 1 over R. So, this R is playing a major role in terms of the diversity gain and the coding gain. So, for the first time it is very explicit that a space time trellis code is going to give you both a diversity gain and coding gain. Okay. So, diversity gain tantamounts to the slope of the BR curve, and coding gain is the kind of the left shift of the curve. So, we get both diversity gain and coding gain from space time trellis code. And now, with this expression we can formulate the rank determinant criteria. What does the rank criteria say? In order to achieve the maximum diversity advantage, the matrix A C comma C tilde has to be full rank, okay, because R was the rank. So, we have to find this C and C tilde, we should design such that we should have this to be full rank, and suppose A is full rank, then in order to achieve the maximum coding advantage, the minimum determinant of A over all possible C and C tilde should be maximized. So, this is known as the rank determinant criteria. That was for slow fading channel, and if you do a similar analysis for fast fading channel, you get a parallel set of design criteria. So, you can first show that what is the pairwise error probability for fast Rayleigh fading channel. The expression comes out something like this. So, the rank R term is missing here. Now, the minimizing the PEP leads to the following design criteria for fast fading channels. First, we have the distance criteria, and then we have the product criteria. Therefore, they are called the product distance criteria for fast fading channel. In order to achieve the diversity NH and R, we require any two code words of C and C tilde such that the minimum symbol wise Hamming distance between C and C tilde must be at least NH. So, this will give you the diversity of NH and R, that is number 1, and the product criteria again coming from the PEP expression is to obtain the maximum coding advantage, we have to maximize the minimum of the products as follows. So, this can be done by simple search algorithms to find out good mapping. Finally, it comes down to the mapping. How do we assign the labels, the edge labels of the trellis? So, this is the product distance criteria. With that, we come to the end. So, let us summarize. We have looked at how to compute D free, then we went to study TCM for fading channels, then logically we went into space time trellis codes and looked at two scenarios, slow and fast Rayleigh fading channels, and we looked at a couple of examples. With that, we come to the end of this lecture.